Let's take another example. Give the simplest logic circuit for following logic equation where D represents don't care condition for the following locations. Functions A, B, C, D, summation, minterm 7 plus don't care condition 10, 11, 12, 13, 14, 15. In this location we will write the cross, in this location we will write 1, other location we will write the 0. So let's make a K-map. Here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So here it is written 10, 11. First of all, in this location we will write the 1. In the 7, location is 7. So 0, 1, 2, 3, 4, 5, 6, 7. Here is 1, then 8, 9, 10 is 10 is cross, 11 is cross, 12, 13, 14, 15 it is cross. In remaining location we will write the 0. Okay. Now we will make a group with 1 and cross. Consider like 1, 1. We will make a group corresponding this changing A bar to A, so we will not take A. The common is B. We will take B vertically, and for this it is this corresponding variable CD. So B into CD, y is equal to PCD. From this equation you can draw the circuit diagram BCD and get output is Y. Important points. First of all, given the truth table, draw a K-map with 0 and 1, 1s and don't cares. Zeros, 1s and don't cares. Then encircle the actual 1s on the K-map in the largest group you can find by treating the don't care as 1s. After actual 1s have been included in the group, discard the remaining don't cares by visualizing them as 0. Like we use this one, this don't care. Consider this is 1, 1. The remaining one we will discard it. Like that. The product of sum. We learned the sum of the product. Now the product of sum. The product of sum method is similar like sum of the product. Given a truth table, you identify the fundamental sums needed for logic design. Then by ending these sums like A plus B plus C like this, you get the product of sum equation corresponding to the truth table. The sum difference are there. With sum of the product method, the fundamental product produces an output 1 for the corresponding input condition, but here the product of the sum method, fundamental sum produces an output 0 for the corresponding input condition. So it is a like reverse as compared to sum of the product. The best way to understand this distinction with the example. So this is the example. The fundamental sum of these inputs like A plus B plus C, product of sum Y. So here you can see one truth table, but here is we know the fundamental sum produces an output 0 corresponding input condition. So that's why here this is not this is A bar, but this is A, this is B, and this is C. This is 0. A, B, C, output is 0. Okay, we will only consider these zeros for the product of sum. Another, here is also it is output 0, so this one is A, this is B bar, this is C bar. It is opposite to sum of the product. The product of the sum is opposite to sum of the product. And plus, and in addition, we need to put, instead of multiply, we need to put plus sign here. So this is A, B bar, A plus B bar plus C bar. Output is 0. Another is here, output is 0, so this is A bar, B bar, A bar plus B bar plus C. And this is the max term for the product of sum. These are all the max terms. So M, capital M, M0, capital M1, M2, M3, M4, M5, M6, M7, like this. So this is the product of the sum. Now, how to convert from the sum of the product to product of the sum, or product of the sum to the sum of the product? First of all, identifying the complementary locations, opposite locations, changing min term to max term or reverse, changing summation by product or reverse. Okay, so let's take example. Y is equal to function ABC, and this is the product of the sum pi capital M 036. So what is the remaining term, or the remaining locations, like pi M 036? So if we convert into the sum of the product, sigma M 1, 2, 4, 5, 7, 1, 2, 4, 5, 7. So table 3.9. So this is table 3.9, right? So this is 1, 2, 4, 5, 7 related to 1, 2, 4, 5, 7 related to sum of the product. Okay, and this is related to product of the sum, this one. Now another example, y is equal to f function ABC. This is sum of the product sigma M 3, 5, 6, 7. So whatever the locations not covered included here, we need to write here, like pi M 0, 1, 0, 1, 2, 4, 0, 1, 2, 4, pi M 0, 1, 2, 4. For the table 3.4. So this is for the this is 3, 5, 6, 7. It is sum of the product, but 0, 1, 2, 4. 0, 1, 2, 4, the product of the sum. So we can convert from SOP to POS. Sum of the product circuit. From this truth table, we can write the K-map. From this K-map, we can make the 1s groups and quad. We can write the equation. Let's write the equation. So here, this for the horizontal, this A bar B bar, and here is changing from C bar. This one is C bar D bar C bar D C D C D bar. So only we can write the variable here, A B bar plus another group here, A B plus another group, this squared. So this one here, A is common, so A and here C is common, so C plus AC. From this K map we can write the equation AB bar plus AB plus AC, and this figure we can write this one as a NAND gate A bar B bar AB AC. One first, second, third NAND gate is connected to final NAND gate. This is NAND gate circuit. Now to get a product sum circuit, we will do the complementing each 0 and 1 on the K map. Means we will write the complementing. Instead of 1 we will write here 0, instead of 0 we will write here 1, and we will make another K map. So here we put the 0, here we put the 1, here we put the 0, here we put the 1. Then again write the equation, so A bar B for this, and for the another group AB bar, and here is common C bar, so plus AB bar C bar. Okay, so this is total 3 gates A bar B, A bar A, B bar, C bar, which is connected to another NAND gate. We know that from the original truth table, D. Morgan's first theorem tells the NAND gates can be replaced by the bubble OR gate. Therefore, we can replace this 3.20D into 3.29D. So this is step first, second, third, and this is final. So 3.28T, this will convert into this NAND gate convert into the NOR gate. How? Like this. First of all, we can write this circuit like this: A bar B, A B bar C bar. The final output is Y bar. Then we can write this circuit with a complementing. Instead of A bar, we write A B bar, A bar B C. This is as it is. Then we will put here the bubble. Then similarly A B bar B C. And the final step, we will put here one bubble, and this Y bar will convert into the Y. So A B bar B C, and this is Y. If we use the dual theorem, we can directly write this equation in this form. Only we put the complement, like here the A B bar B C. Instead of NAND, we will write the NOR if we use the dual theorem that we will use later. Duality. An earlier section introduced the duality theorem of Boolean algebra. Now we are ready to apply the theorem to logic circuits. Given logic circuit, we can find the dual circuit as follows: change each AND gate to OR gate, or OR gate to AND gate, and complement all input-output signal. And we can also change each NAND gate to NOR gate, or NOR gate to NAND gate. So whatever we have done here, this is the steps. First step, convert the truth table into K-map. Convert the truth table into the K-map. After grouping once, write the sum of the product equation. After grouping once, write the sum of the product equation. Draw the NAND circuit. This is the sum of product solution for Y. Draw the NAND circuit. This is the solution of NAND solution of Y. Then complement the K-map here. So this is the complement from this K-map. Again write the equation. Again make the complementary NAND circuit. Convert the complementary NAND circuit to equal dual NOR circuit by changing all NAND gates to NOR gate and complementing all signals. What remains is the product of some solution for Y. Okay, from this to this. Compare NAND circuit step 1 with step 3 NOR circuit. You can use whichever circuit you prefer. Usually the one with fewer gates we will use. In simple circuit we will use. Let's take one example. So the sum of products and product of some circuit for K-map figure 3.30a. Figure 3.30a. So let's make a grouping of ones. So this is one octet and this is one pair. From the octet it is the common is A plus, and we will not take any variable from this because it's continuous changing. So we will take only common A plus from this pair, the common is B and CD bar. A plus B CD bar. Now from this equation we will write the we will draw the circuit. So B C D bar NAND gate. Here is A NAND gate. The output is Y. Now we will make a complementing K-map. So complementing K-map is 1 1 1 1 1 1 0, and again we will make a group, one quad, second quad, this horizontal group, and this is the overlap. So if we make the equation for this one, here common is A bar, or we will take first this group. So A bar B bar, for this one A bar B bar. For this horizontal we will not take any variable from here because it's a changing. So A bar B bar plus, for this quad it's A bar and C bar, plus for this quad it is again A bar and D. So from this equation we can draw the circuit A bar B bar plus A bar C bar A bar D. NAND gate output is Y bar. From this circuit NAND gate we can complementing and write the NOR gate AB, AC, AD bar, and final output is Y. So next lecture we will discuss the logic family. Thank you.